In this problem, we look at leakage effects associated with real capacitors. Important concepts include the capacitor voltage when discharging through a resistance, and the capacitor energy. Let's review the basic facts from the problem statement. We learned that the dielectric materials used in real capacitors are not perfect insulators, and a resistance, which we call leakage resistance, in parallel with the capacitance can model this imperfection. Let's see if we can understand this with a picture. I'll draw two parallel plates representing a parallel plate capacitor. We have some insulating material that separates these two plates. We call this the dielectric material. Now when the capacitor has been charged to some level, then we see charge displacement such that accumulation of charge exists on one plate and a deficit of charge exists on the other plate. So whenever we have charge separation like this, there's an electric field that exists inside the dielectric, and since the dielectric is not perfect, we can have some of the charges moving directly from plate to plate through the dielectric. This leakage actually discharges the capacitor eventually. Now, to study this phenomenon, we can model the physical situation by first placing an ideal leakage-free capacitor and then using a resistor in parallel with the capacitor to then provide a path for current that goes from one plate to the other. Again, this resistor is really a property of the dielectric itself, but we model it with a resistor that we can discuss individually. So the overall voltage I've noted there across the capacitor is V sub C. Now, a discharging capacitor has the equation of the form initial voltage, that's V sub I, times e to the minus t over RC. V sub C is a changing value over time, and it's also the form of a decaying exponential. It begins at the initial voltage V sub I, and then gradually decays towards zero. The rate at which it decays is governed by the time constant RC. Now we'll say that we have a 100 microfarad capacitor initially charged to 100 volts. What we'd like to have happen here is that 90% of the initially stored energy is still in the capacitor after 1 minute, or 60 seconds. Let's think about that statement about energy for a moment. In general, capacitor energy, designated as W, is 1/2 the capacitance times the square of the capacitor's voltage. Now initially, we have the statement that the voltage is 100 volts, or we're using that symbol VI for that purpose. So we say that 90% of that starting energy value is what we want to have at 60 seconds. Or we are saying it should lose no more than 90% of that value. We can then calculate a new voltage corresponding to that energy, and so at some future time we would be able to calculate the specific time at which the voltage hits that 90% energy related voltage. This gives us the limit on this resistance, and we can then solve this equation for the resistance R. All right, we are ready to move on to the details. Let's begin by calculating the initial stored energy based on the problem statement. Capacitor energy is 1/2 times the capacitance times the square of the capacitor voltage. Initially, we are using the voltage VI, which is 100 volts. The capacitance is 100 microfarads. That would be 100 times 10 to the minus 6. And 100 volts is squared. All right. You could punch this out on your calculator, resolve all the various exponents, and find that you have 1/2 joule in the capacitor originally. I'll use W sub F to indicate the final energy. We're trying to find that value V sub F, the final voltage. So we can say that the final energy is supposed to be no less than 0.9 times the 1/2 joule that we had originally. Therefore, we have the expression for energy equated to 0.45 joules. I'm going to put the 2 on the other side of the equation, divide through by C. Again, C has the value 100 times 10 to the minus 6. Take the square root of both sides, and resolving that to a number, we have 94.87 volts. So it looks like dropping 90% of the energy means that we went from 100 volts to just a little bit less than 95 volts. Now, when a capacitor discharges through a resistance, its voltage Vc has the form V sub I times e to the minus t over Rc. So we can say that at the end of a 60-second interval, or that's the same thing as 1 minute, then we know that the voltage has that final voltage level of just under 95 volts. We have enough information then to solve for the associated resistance. Let me put V sub I on the other side of the equation. I can then clear the exponent by taking the natural log of both sides. So natural log undoes the exponential operation there. Redraw that a bit, and we're trying to solve for the value R. I'll bring that on the left side of the equation, and then bring natural log of this ratio to the denominator of the other side of the equation. Let's go ahead and drop in the numerical values. And when you enter all these numbers into your calculator, you have 11.39 mega ohms. So as long as the leakage resistance does not fall below this value, then we satisfy the problem requirement. Let's review the overall problem-solving approach we followed. First, we needed to determine the initial stored energy, knowing the initial capacitor voltage. We then calculated 90% of the initial energy and its associated capacitor voltage. We then recalled the equation for the voltage of a capacitor discharging through a resistor, substituted the voltage at 90% energy and 60 seconds, then solved for the minimum required leakage resistance. And that wraps it up for this problem.